so I've covered analytes that all kind of have similar potentials to dopamine. But in this little segment, I'm going to cover some of what I call the higher oxidation potential analytes. They're not really a group, but they're things that we can see, and they don't look like dopamine. So there you go. We're going to start with the Denison, because this is something our lab has personally spent a long time looking at. And adenosine, okay, I'm going to draw some structures. You'll find these better in our papers, so if my writing isn't very good here. But I want to look at, oh, I need those connected. I need an H2 up there. And then, oops, I didn't draw the second ring, that's why. All right. I haven't taken orals in a while. I haven't drawn these from my head. Okay, this R is a ribose group. It's a sugar. We're going to ignore it. I'm not going to draw it. But this is the ring structure where we're going to get all the oxidation stuff happening for adenosine. And so the very first H+, and we need to add on a water. Is that we're going to oxidize here. And we're going to add in a double bond O there. The rest of this. Not going to look that different. Okay. So we add in the water to add kind of an OH bond there. So that's the first oxidation point. This potential is fairly high. I think if you looked up an E0, it'd tell you it's about 1.3. Again, in FastScan, all those potentials get shifted because we're going super fast. And so I should say that, like, whenever I want to look up any of these mechanisms, these papers from like the 80s by a guy named Glenn Dryhurst are like the bomb for all of these kinds of things that I'm showing you. He wrote a book, and it just goes from molecule after molecule showing you all the electrooxidation things. That stuff never goes bad. It doesn't matter when he did it, it was great work. Kind of thing. Also, he was from Oklahoma or something, some Midwestern university. Electrochemists can be great, and they don't have to be at Harvard, right? You can get all this great fun in electrochemistry work coming out of small colleges, coming out of, Midwestern places, anywhere, Virginia, hey. But it doesn't matter. All right, so that's our first oxidation for adenosine. And then we can do another oxidation. And now we're going to oxidize here. That's going to be the site that we oxidize. So this ring structure is going to stay the same as last time. I'm going to get all my double bonds in the right spot. All right, I'm going to get my 5-membered ring. We're going to add all of these. Again, are a little more complex because we're adding water to add those oxygen groups. So my end back in there. So we're going to do that. So so once we oxidize on the 6-member ring, the next time we're going to oxidize on that ring. Ooh, right? Yeah, I'm good. And then we're going to oxidize one more time. And now we're going to oxidize here. And so I'm not going to add a water this time. One more time. NH2. This is at the 7 going to end up being the same. Okay. And so we're going to get one last product. All of these reactions get easier. If that one's about 1.3 in FSCV at least, this one shows up about 1.0. If we were to see this one in FSCV, it would show up, I think, around 0.5, something like that. So this is the hardest one it ends up to do. And so for adenosine, our cyclic voltammogram, that we typically see just these first two. And so if you were to do one cyclic voltammogram, you have perfect adenosine in there, you'd go up. Typically, because we only scan out to 1.45 volts, so a waveform for adenosine is typically minus 0.4 to 1.45 volts at 400 volts per second. So that's our typical waveform. As we scan out, typically, just because of the time delay between when we hit the potential, we could do the electron transfer, and when we actually see it at the electrode, we actually see these peaks on the back scan. Now it's really hideously drawn. And maybe a tiny reduction peak, but typically not. So we get this peak, but it's mainly at the switching potential. If, however, we start to accumulate oxidation product, maybe because we don't reduce it back, it can go on. And so in future scans, what we actually see, a more typical one would see, I'm going to draw this kind of with an extra peak there and not much reduction. So we'll see a primary peak and a secondary peak. So this is the primary reaction, and that's the, I skipped the primary. It's like something's not right here. This is the primary, and this is the secondary. Right, so we see two peaks, and that's really useful. So just a point in life that's just practical, nothing to do with real like formal logic. If you want to identify something in the brain, having two peaks makes you a lot more likely to know what it's looking at than it just having one, right? Because a lot of things maybe could have that same peak, but like that's why it's like, oh, it's helpful to have an oxidation and a reduction peak. Well, here we don't have a reduction peak really, but we got two oxidation peaks, and it's just practically a lot more easy to say, oh, I know what I'm looking at if I have those two peaks. Also, if we do a color plot, which I'm now going to attempt to draw poorly, one of the things you'll see, as I said, is there's a slight delay in this peak. And so, again, right at the switching potential is where we tend to see adenosine oxidation. And then the secondary peak will kind of often grow in with time and be a little time delayed. So in a color plot, again, a reminder that time is on this axis, applied potential is on this axis, and color, and here I tried to draw it as green because that's what it looked like on our color plots, would be oxidation. So the color tells you about the oxidation. So we have kind of two green peaks here, and the secondary peak, which is this one, is usually delayed. So our group, again, wrote an automated algorithm to detect this in the brain, and we decided to use the color plot because the CVs can change over time. The size of this secondary peak can go way up and down compared to the primary peak. But this is a very good signature in like an image form of what adenosine looks like. So we used image analysis. So that's adenosine, and we've done a lot of work on that. Ashley Ross's group, actually we did this once just to do it, has done guanosine. And I want to throw this up there because I want you to see the starting structure of guanosine is this. Let me draw it and then we'll talk about how it looks. Okay, I drew it here for a reason. Where did my R go? That's not an H, that's an R. I was like, okay. Guanosine, as you notice, is just the flip, basically, of the middle product of adenosine oxidation. Like here you have the double bond O and the NH2 kind of coming around. Those are flipped compared to this one. And so when you look at them, if you ever look at guanosine doesn't really look like adenosine. It's got an extra double bond O. It looks like that one. And so maybe it's no surprise that the oxidation is basically the same as this middle step for guanosine. And so when they get to the oxidation, Again, we've already done that double bond O, so we're not going to do much on the 6-membered ring here. Instead, we're going to end up with the double bond O on the 5-membered ring. And so, if you were to predict where the FSCV would be, you would predict it would be about the same place the secondary peak is on adenosine, and you would be right. And so again, this is where I think sometimes maybe our lab doesn't delve into the structures enough. I'm not actually all that great at them. But when you look at the structures, you're like, oh, look, same. Samesies, right? You know, just switching where the functional groups are. And so the FSCV for guanosine is similar. You can also do this same reaction. I'm getting lazy, don't feel like drawing it. For a third one, and so for the guanosine, what they end up getting for guanosine FSCV is they'll get a secondary peak down here and a primary peak more like here. And actually for guanosine, they don't even usually scan out to 1.45. You don't need to. You'll get your peak at 1.0, and again, another peak may be down at 0.5. Sometimes, if there's ever a reduction peak, it's on this reaction. This might be the only one that's slightly back. So yeah, so there's a good old guanosine CV. And again, it's all purines, but it's like you're starting in the middle. Like we skipped this reaction, we restarted there for guanosine rather than adenosine. So not surprising that you can see similar electrochemistry as you go. So any good chemist might say, what about ATP? Right, adenosine, but now let's add on the phosphates. Okay, any of them, AMP, ADP, ATP. There's a problem, and that is that the electrochemistry isn't going to change, right? The phosphates are there. This part's still the A, that's going to do that. But because of absorption, it turns out that our ATP sensitivity is about 4 to 6-fold less than adenosine. So we can see ATP. We find that we see a little bit difference in the ratio maybe of primary to secondary, but you can see it. I just feel like I need to admit that. You'd see GTP too. Good old, like adding the phosphates. But I think just how it lines up on the electrode, those phosphates tend to kind of mess with the surface chemistry just a little bit. So as I said, you got to be able to scan up to at least 1.45. We don't scan higher because, again, of water oxidation. We don't want to do a lot of water oxidation in the brain. So that the first paper we scanned to 1.5. Then one of my students said, I think I'm seeing a little bit more water oxidation, which leads to an unstable, especially if you get water oxidation and this is the background, it leads to a really unstable peak here. And he backed off to 1.45 and said, it's good enough. I see plenty of signal. And that peak goes down a little bit, and I think it's more stable. So if you are a real fan of the Denison literature and the vet lab, you can see we slightly changed our waveform after a paper or two to make it a little bit more stable. But that's what we typically do now. Okay, that's adenosine. And guanosine, its friend. Those are all called purines. And again, there are other purines and things that are related to purines, uric acid, other kind of, derivatives of purines. And again, if you looked at the structure, you could probably say, are those, places available to do oxidation that are available on guanosine or adenosine? How we predict whether it be electroactive. All right, let's go under a few more of these higher potential ones. Let's do histamine. Okay, so histamine is another one that I hinted we're going to have issues with because it's got, we're going to end up doing a 1 electron oxidation. I guess it's not a 1 OH, but we're going to end up doing a 1 electron oxidation. Okay, this one has an H. There we go, and then we've got a amine group sticking off here. And so with this, again, one electron oxidations are tough. If we lose one electron, we're going to lose it on the nitrogen. And so we're going to end up with a kind of nitrogen radical species here. Same. I put it on carbons. Yeah, 1, 2. Yeah. Same sort of thing. So you can lose an electron. It's not that hard or kind of thing, but the problem is that this is really unstable. Again, radicals are unstable. And so if you have another one of these, which I will attempt to draw backwards, these can react and they can form a dimer. And it turns out you can keep doing this. You can keep dimerizing. And so histamine's very good at forming polymers. So I should have written that this initial reaction, again, I'm not always writing you E0s. E0s will be lower than what we see in FSCV. For here, in FSCV, we see it about 1.3 volts. And we've done extensive work in our lab to show that you can't see signals at lower voltages than that. So you can form this dimer and polymerize. And so again, polymers are not our friend. We don't want to make polymers. Is not particularly reversible. And so again, FSCV for histamine might look something like this. If we only scan out to 1.3, the peak will often be on the back side. Occasionally we'll get a little bit of a secondary peak as well from some downstream oxidation of this polymer. And so we'll see occasional lower peak as well, but the peak itself is at about 1.3. If we were to go out to 1.45, we can sometimes get it on the front scan. So it just depends. You can see it without going out to 1.45, you can see it at 1.3, but there, again, the electrons transfer is going to be delayed, and this is kind of where people tend to see it. So histamine is kind of nasty, kind of like serotonin in the fact that if you make a lot of this polymer, you lose your sensitivity fast. So histamine is, again, another super fouling kind of problem waiting to be had. And so we did some paper, when we wrote a paper on this, we did some experiments, but I mean, you see, here's what I get the first time, and the next time I get 50% of that or something. You know, if you made that polymer, it just really sticks to the surface. So Nafion coating, again, maybe could help with that, just to help not have things stick as well. Or again, scanning out to like 1.45 and trying to clean the electrode surface, or holding something that's going to clean the electrode surface is going to help as well. Okay, so that's histamine. Slightly lower potential than adenosine, but still kind of around the same one. Again, we're not super great at telling apart things that are kind of similar. Also out there in the 1.3 to 1.4 range, hydrogen peroxide. So again, hydrogen peroxide, you can make oxygen plus 2, hydrogen plus 2 electrons, right? So we lost those. For an oxidation, again, hydrogen peroxide, people look at this reaction all the time now for fuel cells, right? The oxygen reaction, you know, it's the backwards part, you know, et cetera, et cetera. So this is a highly studied reaction. But where the Somers group figured out and where they wanted to go was to use this also in a biosensor kind of fashion. So hydrogen peroxide is also a product of a lot of enzymatic reactions. And so if you want to put an enzyme on your electrode and then have it take our analyte and create an electroactive product. Hydrogen peroxide is one of the favorite electroactive products that people use. Again, hydrogen peroxide, maybe one of the good and the bad news is, again, we get some sort of signal out here near the switching potential, typically about 1.3 volts. There's no other peak you're going to get. You should not get any secondary peaks. There's no reductions, it's not particularly reversible on our reactions. And so I said it was easier practically to identify things with 2 peaks. You're not going to get 2 peaks here. You're going to get 1 peak, kind of at the switching potential. But again, it is a biologically relevant molecule. Your brain does make hydrogen peroxide, even without that biosensor part. There are fluctuations in hydrogen peroxide that Leslie Saunders has looked at, Margaret Rice has looked at, some other people in the field. All right, let's look for a minute at amino acids and peptides. So peptides are just short chains of amino acids. I'm not actually going to talk about any peptides here. No, I guess I am going to talk about peptides. I take that back. I'm going to talk about encapsulated. But you start with the electroactive amino acids. And there are only a few. Most amino acids are not electroactive, and that practically means we can't oxidize them in the range that we see, which is about up to 1.5. But tyrosine is, and I'm going to attempt to draw tyrosine, not probably well. So down to the amino acid kind of part. This is if it was in a peptide there, we got the peptide backbone kind of going here, something else that it would be there. So right, this is the side group, basically, for tyrosine, and it can lose 2 electrons and 2 protons, and we can, maybe not surprisingly, you saw that dial on there, go to one bond. I'm just drawing horribly. Let's actually hold on to now. And then again, we're to the backbone part of our amino acid. That's not. Okay. So we can do an oxidation because we have, again, that ring kind of structure. Typical, again, potentials for this that we see in FSCV are potential around 1 volt. Sometimes we see extra peaks as well. Quite frankly, the event lab's trying to study this now. We're still trying to figure them out. But you can sometimes see some downstream things. And if you put in a trapping electrode, you're going to see even more of those. If you put in a carbon nanotube yarn or something like that. But tyrosine we can see. We don't think tyrosine has the best sensitivity. I'm going to show you tryptophan in a minute. And I think if tryptophan and tyrosine are both in a peptide, I think the tryptophan is going to be easier to oxidize than the tyrosine. Again, so just the amount of current that we get is not that great for tyrosine. I don't think our electrodes are that sensitive. So maybe that's a good challenge for somebody. Develop a better sensitivity electrode for tyrosine. Okay, tryptophan. Now, tryptophan has a double ring structure. Again, I'm trying to figure out how to make this draw. Side group. Again, we're going to go down to the amino acid structure here, but here. So we got the amino acid structure. Oops, I didn't really finish. There you go. With the tryptophan. And typically when it's oxidized, we're going to add water again as well. So this is kind of similar to the adenosine ones. Maybe you can see, again, start to see some of the structural similarities. Where we're going to now add water here. Let me go back. Oh, actually, it doesn't actually do that. At least in the one that I have drawn out. There's many forms that we're going to do that. And then this we go back down to the bottom that I don't feel drawing. So we're going to oxidize the ring there. This also has a very similar kind of FSCV potential, somewhere around 1.0 to 1.2 volts. It's typically where we see it. So higher than dopamine, kind of upper level thing. I think, again, just from our practical work, that the tryptophan's a lot easier to see. We get more current for tryptophan than we do for tyrosine. I don't know. Even though the electrostatics of like the energy is about the same, but man, I get better current for tryptophan than tyrosine. And then Leslie Songer's lab has done one more. Those are the two main ones. But they've done some of the ones that include cysteine, and so they've done methionine. And the mechanism I found here wasn't very good. Maybe I should have kept looking. But now we've got the sulfur, right? And so you can oxidize on the sulfur as well. And a mild oxidation on the sulfur is that. Amino acid. If you really do over-oxidize, you can actually do this as well. You put two of them on there. I don't think in her FSCV she's doing that. She finds that this reaction happens, again, around 1.3 volts. And so she's used this to tell apart met enkephalin from leucine enkephalin, where they're the same peptide, but they have one amino acid different. And so for met enkephalin, my brain will work enough to show it. If she scans out, she'll get a peak at the switching potential, and then she'll get a peak a little bit lower for that happens to have tyrosine in it, the enkephalin does. So she'll get two peaks, but if you were to do leucine enkephalin, she would just get one peak, kind of not at the switching potential. Yeah, those are really approximate. That should be at the switching potential, that should be lower than switching potential. So this would be met enkephalin, and this one would be leucine enkephalin. And so she's done a fair amount of work showing that, yeah, if you use that methionine peak, you can tell apart two peptides that are one different. She's also done some multi-scan rate things. So again, you can take some of these things and they might cause fouling again on the electrode. And so she's developed a waveform for her met enkephalin that looks something like this. Where for this part, she goes slowly, so she basically, you don't want to pick up, if you go slow scan rate, you don't pick up kind of interference and other kind of things that are going on. Near where she's expecting to pick up the tyrosine, she then picks up the scan rate to 400 volts per second, and then she holds, I think for 3 milliseconds at the top, because she wants to see that methionine peak, and then she comes back down, I think it's 100 volts per second. She calls this like multi-scan rate voltammetry or multi-scan rate waveforms. But I just thought I'd put one up there because people are really like trying to optimize for different analytes. They're trying to optimize different waveforms. So she's been able to do this for kind of peptides. And as I said, the way the research always seems to go in this field is kind of like carbon fibers, dopamine first, new electrodes, dopamine first. Okay, back to carbon fibers, maybe some other analytes. Now, I think where the field is going, if you had my own personal opinion, it's, okay, maybe some other electrodes or other waveforms, right, with multi-op analytes as well. And so I think in summary, there's still a lot to be done. to kind of optimize these other things. And of course, there's tons to be done, because I haven't talked about it at all, about telling them apart. That's going to need more informatics, machine learning, that kind of thing. That's a place I think the field is definitely going to go. Because while we can't maybe distinguish slight differences in shape or whatever, if they're real and they occur over and over again, a computer can probably pick them out. And so, but again, the mechanisms are harder. Sometimes just like getting a stable signal can be harder. And then the biology for all of these things is harder. And we did one paper in our lab on GnRH. And someone's like, I don't understand how you could ever say that was GnRH. There's so many peptides in the brain. It's like, yes, but I was looking for a peptide that was released and taken up pretty quickly. And so GnRH is a fertility hormone that tends to surge, to regulate different types of, especially female cycles. And so it's like, yes, there's a million peptides in the brain, but most of them aren't changing on the time scale I want to look at with FSCV. So if you can find, you have to design your experiment well. But if you want to find it, you can find one that's surging, yeah, you can probably be able to look at it. And so it's kind of fun to expand FSCV, I think, past dopamine and look at some of these other amyloid